All right, so on this video, we're going to talk about the first of the techniques of integration we'll discuss, which is called integration by parts. And it's the first of the four we'll discuss this semester. Integration by parts. It's a pretty standard Calculus 2 topic. It is used primarily, pieces of information, and we'll talk through it a little bit, and then we'll go through several different examples here. So it is used primarily if the integrand, that is to say the function you're integrating, is the product of two functions. That is to say they're multiplied together. Especially if one is transcendental if one is transcendental, and when I say that, I should say at least. They might both be transcendental, but at least one of them is transcendental. So the question is, what might that look like? Well, here are some examples of what that might look like. So, one, we might have, what do I have in my little example? I have x. This is the standard that everyone begins with. Probably every calculus class in the world goes through this example on integration by parts. This is the product of two transcendental functions. When I say transcendental functions, it means a little more than this, but roughly speaking, for our purposes now, that means any function that involves trigonometry, any function that involves inverse trigonometry, the inverse trig functions, any function that involves logarithms, and any function that involves exponentials. So any function, again, this is a little more, it's more than this, but for us for now, this will suffice. Transcendental functions are trigonometric functions, inverse trig functions, log functions, and exponential functions. And so if we have the product of two functions, at least one of which is a transcendental function. Well, I have x times e to the x. That's an exponential function. This is a prime candidate for integration by parts. And as I said, this is kind of the stereotypical. This is the archetype. Almost everyone does this in Calculus 2 to illustrate integration by parts. Another example might be something like this. Suppose we have the integral of x times secant x times tangent of x dx. Now you might say we don't have two functions. Well, we can think of this as this is one function, this is the other. So here's a function, here's a function. One of them, at least one of them, involves trigonometry. So that's a candidate, that's a prime candidate for integration by parts. We can also do definite integrals with this. So we could do the integral, say, from 0 to, let's say, pi over 2 of, let's say, x times sine of x. And so that's the product of two functions, at least one of which is transcendental. So each of these, and there are many others we'll go through. We'll go through several examples of this to get you used to this. It's not brutally challenging, but it's just something you need to get used to. All right, so the procedure is this. We are going to break each of these. So let's take this one as the example here. We're going to break this down into a collection of parts. And they're going to be really two parts from which we're going to generate four pieces total. We'd write this. We would write u, du. We would write v and dv. So we're going to create, or we're going to break this integral down into u and dv. We will generate the others, but for now we need to express this as a function times a differential. Now there's a rule of thumb that comes into play here, and this should hold you in really good stead. We choose dv to be the most complicated function whose integral, or let's say antiderivative, now pretend you can actually read my handwriting. You choose dv. This is the first selection you make. Choose dv to be the most complicated function whose antiderivative you know. Well, there are two choices on offer here. There is the function x, and there's the function e to the x. Now we know how to find the antiderivative of both of those. We want to choose dv to be the most complicated function whose antiderivative you know. Of the two, e to the x is a more complicated function than simply x. So in this particular instance, we would choose dv to be e to the x, and this is the differential, dv, so dx always goes with dv. So everything present here must be accounted for. And so what do we have now? So dv is that piece. Anything that's left over, no matter how much or how little there is, anything that's left over is u. You don't need to choose u. You generate by default because you choose dv to be the most complicated function whose antiderivative you know, and then everything else lumps into u. Well, the only thing left here is x. All right? So now let's do this. Why don't you pause the video here and go through these two examples and see if you can get this far on each of these functions. See if you can get this far. Just choose dv and u, and then we'll check and see how you did. So go ahead and pause now if you like. All right, so if we're back here, so what I think it's pretty straightforward here. dv, I'm going to run out of space here, dv needs to be the most complicated function whose antiderivative we know. Well, of the two, secant tangent is more complicated than x, and we know the antiderivative of secant tangent. So dv is secant x tangent of x, and then we're going to run out of space, dx. Everything else that's left over is just x, that's u. And the same thing happens here. u, du, dv, v. So the most complicated piece whose antiderivative we know is sine of x, dx. Everything else is u. All right, so that's the process of choosing the parts. Now, once we have dv and u, now we create du and x. The way we do this is straightforward. This is just like an ordinary u substitution. If u is equal to x, the derivative of u is equal to the derivative of x. So the du is equal to dx. We take the derivative of both pieces. Here we take the antiderivative. What is the antiderivative of e to the x dx? Well, e to the x is its own antiderivative. And so now we have the four pieces together. And now comes the big deal. This is the parts formula. uv minus integral v du. That needs to go in your brain. There's nothing for it. You need to know it. You need to learn it. It needs to be there. It needs to be automatic for you. This is even more fundamental than the quadratic formula was in basic algebra. This just needs to be in your brain. You need to piece together the parts uv minus integral v du. I might do a little video here later on explaining where this comes from if you're interested. But as in terms of nuts and bolts, you need to take these parts and construct that integral. uv minus integral v du. So in this case, you just simply multiply u times v. U is x, v is e to the x, minus integral and you put together the pieces. V is e to the x. du is dx. And then proceed as before. X, e to the x minus, I need the antiderivative of e to the x. It is its own antiderivative, and we're out. So let's wind this up here now. We use integration by parts if it's the product of two functions, especially if one of them is transcendental, that is to say trigonometric, inverse trig, log, or exponentials. And then we break into the parts. You choose dv to be the most complicated piece whose antiderivative you know. Right here, the dv was secant x tangent x dx. You choose dv to be the most complicated portion whose antiderivative you know. Everything else is u. From those, you find the derivative in this piece, you find the antiderivative in this piece. And then you cobble together this rule just needs to be in your brain. uv minus integral v du. uv minus integral v du. Or uv minus v du. uv v du. uv v du. uv minus integral v du. Plug those pieces in, finish that antiderivative, and you're out. And so what we'll do next is I'll go through a few videos we'll run through these examples and several others so you get to feel for how this works.